So kinematics and constant acceleration problems are really our first look at the heaviness of the algebra that can be present in physics. Prior to now, in the last couple days, we've had very small equations, a little speed is distance for time, or velocity is displacement over time. But these are a little bit heftier, so it's going to take a little bit more algebra skills and some time to get used to that. And a lot of these are word problems, everybody's favorite type of math. But I do have a sort of a process that I tend to go through that is very helpful with these problems in particular and sort of sifting through those problems. So here's one example. A car accelerates uniformly at a rate of 2.5 meters per second squared from rest to a speed, to some speed, it's a little typo, for 12 seconds. It's accelerating for 12s to some speed. It's accelerating for 12 seconds. And what I want to know is, how far did it go? Now, you know, I have my delta V, I'm sorry, not delta V, velocity is delta x over t. But that equation doesn't do me any good because I don't know what my average acceleration is. I know that at the beginning it was 0, but I don't know what it is at the end. So I'm going to have to use kinematics. I'm accelerating uniformly, so I get to use these equations. So the process that I like to go through is called the guess method. You can see it kind of over here on the left. And it's just sort of a way of organizing this information. I think a lot of people's problems with word problems is that it's just overwhelming. There's so much information. What am I supposed to do? So this helps to sort of sort this out. If you like it, great, use it. If you don't, also great. Use something else. Use whatever works for you. This is just sort of the process that I go through. So the first letter G stands for given. My first step here is to decide, all right, what information do I have? So I start by reading problem. It says the car accelerates. Great, I know that it's accelerating. It tells me it accelerates at a rate of 2.5 meters per second. I know a piece of sort of pertinent information. My acceleration is 2.5 meters per second squared. Moving on, it says from rest. That is a huge keyword. Whenever you see rest, it means that there is a velocity that is 0 meters per second. And in this case, because it's starting from rest, it's my initial velocity. And it says it goes to some speed, and it is doing that acceleration over a period of 12 seconds. So that means my time is 12 seconds. Some people say, well, how did you know what variables those went with? And one of the biggest keys is, what are my units? Time is always going to be in seconds or some unit of time. You're never going to have time measured in meters per second. Acceleration is always in meters per second squared. So when I saw that number, I said, that's got to be my acceleration. And then other keywords, sort of using those English and reading skills to say, all right, what's this saying? Well, from rest, well, that means it's not moving. If I'm not moving, that means I have a velocity of 0. The next step is going to be to decide what it is the question is actually asking me for, asking me about the unknown. What am I looking for? And again, it's just a matter of reading. It says find the distance. Well, that's delta x for these equations. That's what I'm looking for. Next up is the decision of which equation I'm going to use. And I always want to pick an equation that fits the information I have and the information I want. So right now I've got delta x, acceleration, initial velocity, and time. I want to pick an equation that includes all of those, but doesn't include anything else, right? I don't know anything about final velocity, nor do I care. I'm not being asked about that, so why pick an equation that has that in there? So the only equation I'm left with is delta x equals v naught t plus 1/2 at squared. The first S here is substitute. I take all of my variables and I just plug it into the equation. Delta x I don't know, so I'm going to do it in there. So delta x, my velocity initial I know is 0. My time I know is 12 plus 1/2. My acceleration is 2.5 meters per second squared. And my time, again, is 12 seconds. I need to square that. And last but not least, we solve our equation that we set up. So if you take those numbers, let's see, we've got this little bit cancels out. So really all we need to do is take, let's see, move that over here. 12 squared is 144 times 2.5 times 0.5 for that half. And we get a distance of 180 meters. And because this is a distance, we don't actually need to give a direction. It didn't tell us what direction that acceleration was in, so we don't actually have a direction here. This is actually a scalar value, but if you wanted to make it more of a vector, you could say in the positive direction, because that acceleration was positive. One of the things to be careful about with these problems is making sure that you pick directions, kind of like I mentioned before, that are consistent. So here we have an elevator that's moving upward at 1.2 meters per second. And I know that that is going to be my initial velocity. Instead of writing all those out again, I'm just going to label them in the problem. It says it experiences an acceleration of 0.31 meters per second squared. That's my acceleration, but this word here, downward, is important because now I have two separate directions. I've got upward here and downward for the acceleration. I can't have both of those numbers be positive, right? One has to be positive, one has to be negative. Personally, I like to make upwards positive most of the time. There are a couple exceptions. But most of the time, I like to think of up as being positive. So I'm going to make this 1.2 meters per second positive and this acceleration negative. If I don't do that, my answer changes. And it tells me that I go a distance of 0.75 meters. So that's my last given. So I've got my three givens. My unknown is my final velocity. So right now I've got velocity initial involved, I've got acceleration involved, I've got delta x, and I've got final velocity. The equation that fits with that is going to be vf squared equals v naught squared plus 2a delta x. Notice that nowhere in this problem was time mentioned, right? I'm not looking for it, I don't have it, I don't want it in my equation. So now I start substituting. My final velocity, I don't know. My initial velocity was 1.2 meters per second, and that was positive. I'm going to square that. Plus 2 times that acceleration of 0.31 meters per second squared. But I'm going to make sure that it's negative. If I leave that negative out, instead of my velocity decreasing as this process goes on, it will increase, and that's not what's happening. We said in the previous video that if I've got an upward velocity and a downward acceleration, I should be slowing down. If I leave that positive, that's not true. I'm actually speeding up. So I need to make sure it's negative. And last, we've got a distance of 0.75 meters. We've got everything in. We're just going to solve it. So 1.2 squared. It's 1.44. So I'm going to keep that over here, 1.44. So I'm going to do this other bit, 0.31 times 0.75 times the 2. So that's 0.465, but remember that the negative was there. So it's going to be minus that 0.465. So we've got 1.44 minus 0.465 gives me 0.975, but I'm not quite done yet because it's VF squared equaling that 0.975. To get rid of that squared, I take the square root of it, and my final velocity is 0.987 meters per second. And here's where I do need a direction. Because I am left with a positive number, that means I am still in the positive direction. We said earlier that positive was going to be upward, so I am moving at 0.987 meters per second upward after this acceleration.